Okay, so this is discussion of the science for the additional science investigation on falling objects. So if we're going to understand how an object falls, then we need to understand the two forces that are involved, one of which is weight, which is fairly straightforward, and the other of which is air resistance, which depends on a lot of other things. So we need to understand what the cause of air resistance is, and it's basically that when an object falls through the air, it has to push the molecules in the air out of the way. So what we've got here is just a representation of an object with some air underneath it. The NT molecules are in blue, the nitrogen in blue, and the oxygen in red, and they're roughly in the right proportions for air. So when the object falls through the air, it's knocking these molecules out of the way. Now in real air, these molecules are moving around all the time. For simplicity's sake, I've kept them still here, and the object's just going to knock them out of the way. So this is what happens as the object moves through the air. It has to knock them out of the way. Now because the object has to push the molecules down to knock them out of the way, the molecules will in turn push the object up, and that's what creates this air resistance force. Okay? So all of the factors that affect the air resistance force can be explained in terms of how fast the object knocks molecules out of the way. So, first one, speed. Faster an object is falling, the more molecules it hits per second. And also, in this case, because it's moving faster, it hits them harder as well. So there's two sort of things that mean that the faster you're moving, the more air resistance you experience. Next thing is surface area. That's fairly straightforward. If I made that object wider, right, on the screen, so surface area larger in real life, then it would hit more molecules per second, so there'd be more force on it, more air resistance force. The density of the air, if we changed how many molecules there were beneath it, so removed a few and made the air less dense, then it wouldn't experience as much air resistance. So the denser the air is, the more molecules that are packed in there, the bigger the air resistance force is going to be. That might matter, for example, if you were going to very high altitude and doing an experiment, because the air is much less dense at high altitude. And the final factor is streamlining, so the shape of the object. And the way that works basically is that instead of completely knocking the molecules out of the way, if you have a streamlined shape, the molecules are able to flow more easily around the object, and that will reduce the air resistance. So whenever you're talking about air resistance forces and how factors can affect them, you're going to need to talk about the molecules in the air and how they are knocked out of the way. So that's the factors affecting air resistance. We need to put that together now with the weight to try and explain what happens as an object falls. And the basic idea is that you've got the two forces, the weight and the air resistance. And as the object falls, the air resistance increases. So this object, I freeze-framed it, but it was already falling because it already had an air resistance force. If the object has just been released, there's no air resistance force at all. As it falls, the air resistance force increases. You just saw that happen. We freeze-framed it again at the bottom. It is still falling. I've just frozen it in time. At the point where the air resistance equals the weight. Now, the air resistance has been increasing because the object's been falling faster. And speed was the first thing on our list of factors that affected air resistance. So as it falls faster, the air resistance increases. When we get to the point where the air resistance is equal the weight, it can't fall faster anymore. And that's because when it gets to that point, it has zero resultant force on it, so it can't accelerate. Okay, it can't change its speed or direction. So when the air resistance equals the weight, it's not going to accelerate anymore. That means it stays at the same speed, and that speed is what we call the terminal velocity of the object. Terminal because it's its final speed that it reaches. So that's how an object comes to reach terminal velocity. The next important thing is to think about, okay, comparing two different objects, how are they going to fall? So what we've got here is two objects of the same weight, because remember it's really important to control any factors that might affect your experiment other than your independent variable. I've chosen here for my independent variable to use the surface area. So basically I've stretched the object out, okay, but kept the same amount of material in it. So how is that going to affect the way that these objects fall? Well, what we're going to do here is plot on a graph the speed of the objects against time as they fall, okay? And you're going to see a dotted line for the region where the object is still getting faster, right, where it's still accelerating, and a solid line when it gets to terminal velocity. And I'm also going to trace the path of the object where they fall, and again, the dotted part of the path will be where the object is speeding up still, and the solid part of the path will be where it's reached terminal velocity. So if you watch carefully as these objects fall, you'll be able to see how this works, okay? So the small surface area object on the left falls much faster than the large surface area object on the right. They both accelerate to start with, okay? But at every point, the small surface area object is moving faster. So that you can see by the fact that the blue line is always above the red line on this speed time graph. The small surface area object represented by the blue line is always moving faster. Couple of important points to note. That obviously means it reaches a higher terminal velocity, and therefore the blue line stops much earlier in time because this blue object has already hit the ground. Okay? The red line stops much further along the time axis because it takes the large surface area object much longer to hit the ground because it's travelling slower. Okay? Now, that also means that, if you think about it, for the blue object, which is the small surface area one, it won't reach terminal velocity till it gets fairly near the ground, whereas the large surface area object will reach terminal velocity, its lower terminal velocity, fairly quickly. So those are the key points to note. Object with a large surface area reaches a lower terminal velocity more quickly. The object with a small surface area takes a longer time to reach a higher terminal velocity. And similarly, the object with a small surface area reaches terminal velocity closer to the ground, so a large section of its journey, it's still accelerating, it's still getting faster. Whereas the object with a large surface area reaches terminal velocity further from the ground, so it's only accelerating for a short section of its journey before it sort of drifts down steadily. So those are the key differences between two objects with different surface areas in terms of how they fall. What we haven't done is explain why there's a difference. Okay? So, up to this point, we're probably at the sort of BC level of explanation. If you're really shooting for the highest grades, you need to be able to explain why, not just what it does and sort of predict in terms of those balanced forces, but also why it does it. So here's the reason for that air resistance, for those different surface area objects, why they have different terminal velocities and why they will take a different amount of time to fall. So here's the force diagram for our large surface area object. Okay, weight balances air resistance. This is when it's at terminal velocity. Here's the same force diagram for our small surface area object. Now, because they're the same weight, the weight arrow is the same size for both. Right, the arrow representing the weight force is the same size for both. So when they reach terminal velocity, the air resistance force must be the same size for both. Right. Now, here's the reason why then. An object with a larger surface area, this top one here, to get the same air resistance force doesn't need to move as fast. Because it's got the large surface area, it's going to be pushing more molecules out of the way in a fixed amount of time. And so it doesn't have to move as fast to push the same number of molecules out of the way as the blue object, the small surface area one, needs to move. Right? It needs to move much faster to push the same number of molecules out of the way in the same amount of time, because it has a smaller area. So, the blue object will keep accelerating to a higher speed in order to get this air resistance force big enough to balance the weight. The red object will accelerate to a much lower speed to do the same job. So the force diagrams look the same, even though the smaller surface area object ends up moving with a much higher velocity, this green arrow here. So that's the full explanation for why the small surface area object falls faster than the large surface area object. We can do the same thing if we talk about the objects of different weights. So this time I'm going to keep everything apart from the weight constant. All right, it's a good controlled experiment. So for a light object with a small weight force, you only need a small air resistance to balance it. With a heavier object with a large weight force, you need a much bigger air resistance to balance that. So, same thing, because all the other factors, the surface area, density of the air, and streamlining are all kept constant, the only thing that can change to produce this larger air resistance force required to get to terminal velocity for the heavy object is the speed. The speed will need to increase to provide that same air resistance force as that air resistance force being equal to the weight. Right? So for the heavy object, that happens at a higher speed, and therefore it falls faster. Okay, so it's all about linking the factors that can affect air resistance into how fast the object has to go to get that air resistance force, which is quite a tricky thing to do. If you think about it through a few times and be careful about your explanation, it should be okay and that should be enough detail for the highest grades in your quantitative prediction, and also the highest grades in explaining your trend when you get towards the end of the write-up.